Okay, so probably before we start, let me share slides with you guys. And while waiting for that, just want to ask if you guys have any questions so far regarding on what you have learned last Tuesday, basically on linear polarization as well as the introduction of electrochemical impedance.
I have one question.
Yeah, go ahead.
And page 50, 30, 35.
35. Okay.
Yeah.
Yes.
Yeah. Okay. So here there is the inhibitor efficiency is 14, the first one, with the concentration 5 multiplying 10 by, yes.
This one?
Yeah, how I get this number 14? Because if I calculate by using this law, I got 11.
11, not 14.
Yes.
34 minus 30 divided by 34.
Yeah, yes, I got 11.
Oh, yeah. Like 11 or almost 12. Uh, not sure. This is actually taken from a journal. So probably there's a mistake in the calculation. So basically, if you calculate, probably you will get that value. But I'm assuming that the value of resistance RP reported over here, they have like round it off, then probably there's some like change in value as well. Okay.
Okay.
If you calculate it correctly, you should get like maybe answer that you just mentioned to me just now. I mean like 11 or 12. Yeah. Any other question regarding on last week lecture? I mean on impedance. It's just a quick recap maybe before we start. What I've told you, linear polarization method is also known as another method for polarization. The only thing that makes the difference with potential dynamic polarization is the plot. The plot between potential dynamic polarization is more or less log I, log current density versus potential. Meanwhile, for LPR, the plot is basically a normal linear current versus potential. So that is why you're not going to get like a Y shape or T shape of plot that we call as taper plot, but instead you will get like a linear or S curve. All right. The other difference between potential polarization and linear polarization is that the overpotential values, the potential range that been used in LPR testing is basically around plus minus 20 millivolt as compared to potential dynamic polarization plus minus 250. So the reason why LPR use a smaller overpotential range is because we want to get the best linear, because at the lower overpotential values from the equivalent potential, this is where you have a most linear line. Reason also because if you get a very good linear, then the potential or calculating the polarization resistance would be assume success, because if you actually calculate the polarization resistance at the higher overpotential range, then this may have some problem, because a bigger range may be not going to be linear. It's going to be like slightly exponential or what. Okay, right. So the outcome of the results is basically for PD, you can directly calculate or get I-core, corrosion current density. Meanwhile, for linear polarization, you will get polarization resistance first. And then by using a formula, okay, this is basically the formula that I mentioned to you. You can actually calculate I-core. So beta A multiplied with beta C over 2.303 multiplied with beta A plus beta C multiplied with RP, you will get I core. Right. So how you can actually get RP is basically by calculating the slope. As I mentioned to you, the difference between potential over the difference of current density will result you the resistance value. This is actually in accordance with Ohm's law. Right. So some examples. When you actually do linear polarization resistance, you will get those data. RP, beta A, beta C, and then the others will be the values that you already know, equivalent weight and also density of the steel. And when you substitute into the formula, you can actually calculate I core, and from I core, you can calculate corrosion rate based on the formula that you have learned in chapter 3. So this is actually the example if you have an effect of inhibitors and how you can calculate inhibition efficiency based on polarization resistance. So I think last week someone have asked, like, I think maybe Liana, if let's say we have I core from potential dynamic polarization and also RP, which one, from LPR we get or we calculate the I core value. If we want to calculate inhibition efficiency, you can use either one, like RP, or also you can use I core in order to calculate IE. But I think the best is you just directly calculate inhibition efficiency from RP, because if you want to calculate based on I core, you have to calculate first each and individual values, what will be the I core, and then probably later on you have to calculate again the IE. Last Tuesday also, we have started on electrochemical impedance spectroscopy. So the introductory part of EIS, the basic concept, why it is called as impedance, as what I've told you, this measurement is basically using alternating current as the source. So when you have alternating current, then the resistance that will be captured is actually have an influence of capacitor and inductors, because the capacitor and inductors recorded will actually affect the flow of current, flow of electrons. So in other way, if you are doing a DC experiment, the Ohm's law is always going to be like potential is equal to current multiplied with resistance, but in alternating current, the potential is actually equals to current multiplied with impedance of Z. And the data that you will get from impedance is basically in terms of real impedance and also imaginary impedance. The experiment is actually acquire potential static values, okay, a constant potential values ranging from 5 to 50 millivolts. It depends on the samples, but normally for metal samples, people are using 5, even lower, or sometimes if the metal is quite resistant, like stainless steel or what, maybe we can like slightly increase it to 50 millivolt or what. And it is also measured in the range of frequency ranging from 10,000 hertz to 100,000 hertz to 0.01 hertz, or probably lower than that. So the bigger the range of frequency, I think the more information that you get, especially in terms of the interface resistance and capacitance produced. So basically how you can get real impedance and also imaginary impedance. As what I've told you in the experimental setup, you have a cell, and then when the cell is actually been supplied with alternating current, okay, and you set it at a different frequency range, the current values produced during the process is basically will be recorded, okay, since I said to you that the response that you will get is basically in the form of wave-like response, the excitation. So that is why you can get real impedance and also imaginary based on the response of wave that you will get. Okay. For example, if you have a response of wave at one particular point is in a cos theta response, then you know that this basically relates with real impedance. Meanwhile, if you get a sine theta response, wave response, then this will be equivalent to imaginary impedance. And the outcome from these two values, real and imaginary impedance, will result two plots. You have Nyquist plot, which is actually a plot between imaginary impedance versus real impedance, and also you have another one that is called as Bode plot. Right. So the basic concept of EIS, as what I've told you, is because impedance is a useful tool in order to study the interface or the phenomenon that occurs on the surface of the electrodes. So this is actually not been explained for other methods like potential dipolarization and also linear polarization resistant techniques. So from the Bode plot, you can see the formation of how many resistance and how many capacitance that can form on any particular electrodes. So with this information, you can actually predict what will be the interface mechanism or information. I believe I've explained to you whenever we do impedance measurement, the data that we obtain or the plot that we obtain, we need to feed it with a model. The reason why we need to fit with a model is because we want to find the value. So without the fitting, we cannot actually predict what will be the value. In fact, if you read it manually from the plot, it will be complicated. Okay, you will need to recalculate based on the mathematical formulas and whatsoever. So the best is basically we try to fit it with electrical circuit model, that if the data fit with the model, it can give a precise value, and when it is I think fitted with the model, then this actually will tell you that the mechanism of interface is basically follow the electrical circuit design. Okay, so from the interface of working electrode to reference electrode, as what I told you, the formation of a double layer from the migration process and diffusion process basically creates an effect of resistor and also capacitor. So this can be translated from the equivalent circuits that we use for the fitting. And other than that would be the basic concept of impedance, how actually you can read, or what will be the information that you can get from Nyquist plot and also Bode plot. So as I said, for Nyquist plot, you can actually get, or you can see the semicircle, okay? Because the semicircle pattern of a Nyquist plot actually indicates that you have a parallel design in your circuit, electrical circuit. Other than that, you can actually observe how many semicircles that it forms. If you have like one semicircle, then it means that you have one parallel design in your circuit. Okay? You can also see if the points started from the origin. If it starts from origin, then meaning that you don't have solution resistance or electrolyte resistance. The diameter is actually equals to the charge transfer resistance. Okay? So one semicircle indicates that you have one major resistance. And from the Bode plot, actually, you can see the trend or the component from the electrochemical process. If you have like two flat lines, you know that, oh, I have two resistance, and then if I have one slope or one capacitance loop, then meaning that I have one capacitor as the component for my circuit. So with such consideration, with such information, you can actually predict, or you can actually design the electrical circuit that can be used for the fitting. Right. So I guess today we are going to continue the the electrical circuit elements. So far, any question based on my explanation or our recap? Any question? Ada apa-apa soalan? Anything?
So far, okay, Doctor.
Right. So I think we have seen resistor, inductors, and also capacitor. So this is basically the basic component that you'll see a lot in electrical circuit design. EIS data is commonly analyzed by fitting it to an equivalent circuit model. Most of the circuit elements in the model are common electrical elements such as resistors, capacitors, and inductors. To be useful, the elements in the model should have a basis in the physical electrochemistry of the system. Okay. Note that the impedance of a resistor is independent of frequency and have only a real component. Because there is no imaginary impedance, the current through a resistor is always in phase with the voltage. The impedance of an inductor increases as frequency increases. Inductors have only an imaginary impedance component as a result, and inductors current is phase shifted 90 degrees with respect to the voltage. The impedance versus frequency behavior of a capacitor is opposite to that of an inductors. Capacitors impedance decreases as the frequency is raised. Capacitors also have only an imaginary impedance component. The current through the capacitor is phase shifted minus 90 degrees with respect to the voltage. So this is basically the explanation. You will get a resistor if you have mostly a real component, and you will get a capacitor mostly from imaginary impedance value. And this is basically an example of I think a series and parallel circuit design. So imagine that if you have this is actually a Nyquist plot. So if you have a Nyquist plot that actually produce a straight line like this, okay, a straight line, then you know that it will actually produce a series combination. So the total or the equivalent impedance is basically equals to the total or the sum of other impedances, Z1 plus Z2 plus Z3. So for a series connection for RC system, resistance to capacitance circuit, okay, from the Bode plot, you can observe that you have one flat line at higher frequency, and then you have like one slope or one half capacitance loop, which actually indicates that you have one capacitor. And from the Nyquist plot, you also see that it forms a vertical line, not a semicircle. So when you have a vertical line from your impedance, this actually tells you that your design of the circuit must be series in series. So the resistor and capacitor will be placed side by side. Okay. Meanwhile, for a parallel combination, okay, so parallel combination is basically the impedance will be equal to the fraction of other components. So this is basically what you have learned in probably physics, high school physics. You have like one R. If you have a parallel design, one R is equals to one R1 plus one R2, blah blah blah. Okay. So for impedance is also the same thing. Okay. In parallel combination, the impedance is basically equals to the fraction of other components. So you have like 1 over Z plus 1 over Z2 plus 1 over Z3, okay, and others. So for a parallel RC design, mostly it's been seen on the Nyquist plot that it will form a semicircle. The parallel connection of RC circuits. For Bode plot, you will see that it forms one flat line at a lower frequency. Okay. So this indicates that you have one resistor, and then you have like one slope, okay, which indicate that you have one capacitor. Same thing for capacitive loop, or for the phase angle plot, you can see that it forms like half loop. Then this also indicate that you have one capacitance. From the Nyquist plot, as I said, it forms a semicircle. And another thing is that you see that the point is actually start from origin. So when it starts from the origin, it tells you that you don't have any resistance of solution. It's just one type of resistance. Okay? And that is why I think the RC system is being put parallel to each other. All right. A simple equivalent electrical circuit model that commonly used to present actively corroding metals. This, what I've told you earlier. Okay? So if you have a system where metals corrode directly, okay, in electrolyte, working electrodes, reference electrodes, and counter electrodes connected together with a potential stat. Okay. So the equivalent circuit or the design or the Bode plot that you should get is always going to be the same. Okay. So you have two flat lines that actually indicates that you have two resistors. One is basically at low frequency, and the other one is actually at a high frequency. Okay, so this actually your RCT, and this is actually your RS. And you see that you have a one capacitive loop and one slope that actually indicates that you have one capacitor. Meanwhile, for the Nyquist plot, the design that you should get is something like this, semicircle. Just not start at the origin. As I told you, if it is not start on origin, you have RS, resistance of solution, as the first point. And diameter is actually equals to the RCT. Okay? All right. So here we are going to look at one example. It is actually taken from a journal, Corrosion Inhibition Studies of Mild Steel in Acid Medium using plant products as an inhibitors. So from the Bode plot, you can see it clearly. Okay, it has a two. It has a two flat line. One over here, and another one is actually over here. Okay, and you have a capacitive loop. Okay, one capacitive loop, which means you have one how to say capacitance. Another thing is when you look at the Nyquist plot, you see that it is a semicircle, so parallel design should be taken into consideration. But this actually, you will see that it's almost at zero, because your blank is actually very small. So can someone tell me what actually you observe when you have the effect of inhibitors for EIS? This is actually recorded at different concentration of inhibitors. So what is actually you can see or you can observe from the Nyquist plot or from the Bode plot? Can someone actually tell me?
If from Nyquist plots, if we increase the concentration, I have goods like efficiency inhibitor, because the value of Z, real Z, is more than the other. It's 300 almost.
Okay. Then what about from Bode plot or from the phase
Plot,
angle plot?
we can know we have one capacitor and two resistance solution and resistance double layer.
Okay. Anyone else wanted to try? Mariam? Mariam baru masuk.
Doktor, saya terputus tadi.
Oh ya ke? Nazira tak ada Nazira balik kampung dah
Nazira dia tak bangun.
Oh ya ke? I see. Okay, never mind. So anything to to share what you actually see from the Bode plot? I think Mahdi has discussed about Nyquist plot just now. I think I will conclude that later on. But what you can see from Bode plot, Maria? Apart from what Mahdi told, about the electrical component and whatsoever. I'm not sure. Okay, all right. So basically, if you notice that this is a study of inhibitors where you have blank without any inhibitor and with the presence of inhibitor at different concentration. Okay. So probably we can look at Nyquist plot first because it's quite easy to see. So for blank or without inhibitor, you will see that it forms a very small semicircle. This is actually after you overlay. It doesn't mean that you run the whole thing that you get all results. It means that for blank, you run it once, you get one semicircle. For concentration 1 until concentration 3, you run it, and then this is actually the overlay. You just overlay it together. So for blank, you see that it forms a small semicircle. So small semicircle actually indicate what? It indicates that the resistance value is actually smaller. Okay, and if you have a smaller resistance, what does it mean? Anyone still remember? If you have a smaller resistance, what does it mean?
The IE is smaller.
Corrosion rate.
High current.
Corrosion rate is high.
Oh.
Yeah, high current. Actually, if you have a small semicircle, it means that you have a smaller resistance. So smaller resistance, as what I've told you, it means that you have higher current. So if you have a high current, is it good or not good for corrosion? It's actually not good because it's actually accelerating the corrosion process. Then you will observe that the corrosion rate will be higher as well. So that is why over here, okay, small semicircle, it means that you have a low resistance. Low resistance actually means that you have a higher current. And when you have a higher current, then the corrosion process will be faster. Then the corrosion rate will be higher as well. So when you add inhibitors, you'll see that it forms bigger semicircle. You guys can hear me?
Yes, can doctor.
Yes, conductor.
I think I have a problem with my magic pen. It's suddenly not functioning. Mm. Well, never mind. Maybe I just write it. So as what I've told you that if you add the corrosion inhibitors, it forms a bigger semicircle. So bigger semicircle means that you have a bigger or higher resistance. So higher resistance actually indicates that lower current and the corrosion process will be slow. So the thing is, if you add anything or corrosion inhibitors or other types of chemicals, if you notice that the semicircle is larger, okay, then this actually indicates that it have reduced the corrosion process. And as what we've seen over here, from concentration 1 until concentration 3, if you increase the concentration, the resistance will be bigger. So this actually tells you that more amount of inhibitors added, it will actually reduce tremendously the corrosion process. Okay, so the best concentration that we can see over here is basically at 0.5% inhibitors. Okay, all right. Meanwhile, for Bode plot, okay, so Bode plot, as what I've told you earlier, instead of looking at the components, flat line, you have like two flat line, you have one slope, you can actually see the difference as well. The lower one is actually without the presence of inhibitor. This is actually blank. And then when you increase the concentration of inhibitors, you will notice that, okay, the resistance value is also varies. Okay, so this is also in a good agreement with your Nyquist plot. And other thing is basically on your phase angle. So phase angle actually tells you about the rotation. I've told you about the rotation of I think your response signals. But at the same time, it is also explaining how difficult the rotation is. If you have a lower rotation, meaning that you have a lower phase angle or lower angle, and the process is said to be easy, okay? Because it doesn't need a bigger angle to rotate it. But if the rotation actually becoming difficult, okay, with the reason that maybe there's a interaction that retard the process or give a resistance to the process, then the phase angle will be bigger. So that is why over here you notice that when you add the inhibitors, okay, it forms slightly bigger phase angle as compared to the blank. So this actually indicates that you have a very good interaction between inhibitor and also the surface of the steel. Then this actually will give a bigger phase angle or a bigger values of theta. Is it okay to everyone?
Yes, doctor.
Hmm. Um, Having some problem for a while with my PowerPoint slides. Okay. Anything that you want to ask?
Doktor,
Yep.
boleh ulang balik tak yang last tadi? Yang mengenai theta. If you have
Oh,
lower
theta.
phase angle.
Okay. So, let me share again the slides with you guys. I think now the slides it's okay. Okay, right. Boleh nampak eh?
Okay, boleh.
Okay. So now my pen is also working. Right. So earlier I've told you that it forms a small semicircle, and then this actually indicates that you have a bigger resistance. So bigger resistance is actually will result a lower current. So lower current is actually not good. Oh, sorry. Is actually terbalik. Sorry. For blank, small semicircle means that you have a lower resistance. Lower resistance means that you have a higher current. So when you have a higher current, then this will be a fast corrosion process. And when you have a fast corrosion process, then it actually tells you that you have an increase of corrosion rate. So when you add corrosion inhibitors, okay, so what will happen is basically you will see that it forms a bigger semicircle. Bigger semicircle actually indicates that you have a higher resistance. This actually tells you that you have a lower current. So lower current is actually relates with a slow corrosion process. And you will have a lower corrosion rate at the end. For Bode plot, as what I told you, the first one for this plot, the modulus Z versus frequency, you will see that with the absence of inhibitor, is actually producing lower resistance value, and with the presence of corrosion inhibitors produce higher resistance value. Another thing that you can point it out is basically your RS value is almost the same. Okay, so any system, actually, if you use the electrolyte, the same electrolyte, for example, over here, the experiment is conducted using HCl, and then concentration 1 is basically inhibitor with concentration 1 is added to the same concentration of HCl. Others also the same thing, and meaning that you should have a similar resistance of solution, almost a similar resistance of solution. Okay, because we use similar electrolyte. Okay, so you should have almost the same, even though you change the concentration of the inhibitor. The only thing that the inhibitor will change is basically the charge transfer process, the charge transfer resistance value. All right. How about the phase angle? As what I've told you, okay, with the absence of corrosion inhibitors, okay, it forms smaller, okay, phase angle or theta value. So smaller theta value, it means that the rotation, okay, angle is easy. When you have an easy rotation, so it doesn't need a bigger angle, okay, to give a response, right? Meanwhile, when you add the inhibitors, you can actually observe that, okay, the theta value or the phi value is actually bigger. This is actually meaning that the rotation is difficult, slightly difficult. Okay? And it will actually produce a bigger value. So why it is difficult? Because maybe with the presence of inhibitor, the interaction between the inhibitor with the metal surface make it more resistant, and when you have more resistive surface, then the flow of currents and everything will be difficult, then the rotation also will become difficult as well. So that is why it needs a bigger, I think, phase angle values. So bigger, if the phase angle values is bigger, so we say that the interaction between the inhibitors and also the surface, as what I have explained in chapter 3 regarding on corrosion inhibition, you have like adsorption mechanism. So the adsorption process will become, I think the bonding that forms between the inhibitors and also the metal surface is actually very strong. Then you need like more energy or something like that. You need more energy to get the value or to overcome the bonding. Is it okay, Yana?
Okey, doktor. Faham. Okey, okey. Terima kasih.
Right. So in order to calculate the corrosion inhibitors, inhibition efficiency, we can use a formula. The formula is almost the same as linear polarization resistance. What are the things that you need to see is basically the charge transfer resistance. So you'll get this value, double layer capacitance, charge transfer resistance after you feed it. So remember the model that we use for fitting will be Randall's model, Randall's circuit. So this is actually the Randall circuit, okay? And this one, Randall's, simple Randall's circuit. So for any corrosion process, you can actually consider Randall's as the equivalent circuit in order to get the data. So you look at the RCT values over here. Okay? As you increase the concentration of inhibitors, it actually produces a bigger or higher charge transfer resistant value. It is what I told you. I mean, if you add the inhibitor, if the inhibitor is actually efficient at different concentration, then you have higher resistance. So higher resistance meaning that the corrosion process is difficult to occur. Okay, so how you can actually calculate the inhibition efficiency? Okay, so you can calculate the inhibition efficiency using this formula. Okay, almost the same. Resistance charge transfer of inhibitor minus wave resistance charge transfer of blank over RCT of inhibitor multiplied with 100. So for example, like this one, you can get it easily by calculating 315.53 minus wave 19.62 divided by 15.33 times 100. Okay, all right. So the trend is basically when you increase concentration, you will have an increase of resistance. Okay, and what about the double layer capacitance trend? So the double layer capacitance trend, basically if you increase the inhibitors and if the resistance is getting higher, then the capacitance should show a decreasing trend. So you see that this actually showing a decreasing trend, not like increasing trend. Okay. All right. Is it okay to everyone? Okay. Then I put the thumbs up. Okay.
Doctor, the capacity value would decrease with high concentration, not increase.
No increase, decrease, Madi. You will see over here, it becomes
Decrease,
-5.
yeah.
Minus
Yeah.
5. Yeah, -5, this is -4. -5 is actually lower than -4.
Yeah, yeah. Yeah, I thought you said increase.
Decrease. Yeah,
Yeah, decrease.
I say decrease. Okay.
Yeah,
All
okay,
right,
Doctor.
just a quick check to see your understanding. Okay, so between these two inhibitors, so you have like inhibitor A and an inhibitor B. Okay, so I actually run it at the same concentration of maybe acid or maybe medium, and then I put a different concentration of inhibitor A and inhibitor B. So can you guess which inhibitor actually perform the best? Between inhibitor A and inhibitor B.
B. Inhibitor B.
B, Doctor.
I think it's already mentioned over there. Answer. But why? Anyone knows what's the reason? Hamda, you know what's the reason?
When adding inhibitor, it forms
For inhibitor B is what?
inhibitor B.
Okay, so any explanation why? Okay, so don't be, I think, fooled with the shape. You see that for inhibitor A, you see that the shape is bigger. The semicircular shape is bigger as compared to B. But look at the units over here. Okay. Oh, what happened? Okay, sorry for that. Okay, so you have like the maximum for inhibitor A is basically around maybe 125. Meanwhile, for inhibitor B, the maximum resistance value is around maybe, I guess, 500 plus. Okay, so this actually tells you which one is better. So inhibitor B actually produce a bigger resistance compared to inhibitor A, so that is why it's more favorable. This one is more, I think inhibitor B is, in terms of the uh, resistance value is larger or better than inhibitor A. Okay, so still the same explanation. I think and examples of Gambe. I think the previous study that I did during my master's, that's to show you the value that you should get. Resistance charge transfer. This one, CPE. I will explain about CPE now and N value. Okay. So if you notice from this plot, the Nyquist plot from here, if I was a semicircle, but in some cases, we are not going to use randles, simple randles as for fitting. There's a reason for that. Okay. And sometimes maybe if you notice over here, the semicircle resulted from this experiment is a bit depressed. Okay, what does it mean by depressed? If you actually look at the better Nyquist plot, okay, if you want to use simple randles, your Nyquist plots must form like a perfect semicircle. It's like a ball, you slice it into half. Okay, you will use random circuit for fitting. But if you get your Nyquist plot somewhat depressed, like that, or sometimes it becomes just like that, not forming a full semicircle. Like this also, okay? Then we call this plot to experience a so-called depress or depression. So how depression actually occurs? Okay, so depression for Nyquist plot actually occurs due to first
Stance.
surface inhomogeneity. Surface inhomogeneity means that the surface roughness is not even. This actually can be seen a lot if you do due to manual polishing. Okay, as you remember, whenever we want to do any corrosion measurement experiment, we have to polish the plate first. If the polishing is not homogeneous, which means you have like a smooth surface, you have also another part that is not smooth, then this will create surface inhomogeneity. Okay. Other than that, it will be depends on the flatness. The flatness of the plate or the specimen. If it is not flat, then it can also lead to depression. So due to these factors, we cannot use renders, because if you use renders, maybe the fitting going to be like this. It's not perfect fitting. Dotted line is actually from renders. Okay, imagine that this dotted line is actually from renders fitting. When you do fitting, actually it will show like a fitted line to see whether your data actually fit the best with the circuit that you choose or not. Okay, so due to this, you cannot use simple render as the equivalent circuit, but you have to use the so-called renders, still renders, CPE. Okay, what does it mean by CPE? CPE stands for constant phase element. Okay, so for constant phase element CPE design, actually is almost the same as renders, but for the capacitance, it's not going to use CDL, but instead it use CPE, constant phase element capacitance. Okay, the correlation between CPE and CDL is that CPE is actually 1 over CDL. Okay, all right. So when you do the fitting with CPE, okay, you can actually choose the model. Okay, with CPE is normally noted as Q, not C, Q. Okay, CPE. You will get the best fitting data. I think if you try, you see. I think tomorrow or day after tomorrow when you do the fitting, it gives you a very perfect fitting as compared to renders. Okay, all right. So the same observation when you fit the experiment data with CPE. This is actually in the case of if you have like a depressed circuit design, you will have an increase of resistance charge transfer, a decrease of constant phase element or capacitance. You also have N value. N is actually the constant values in CPE. Okay. It also have some explanation if you have like higher N value, high N value that is actually more than 0.85, this actually tells you that the interaction between Ci and also metal surface is actually greater. Then higher of N value also indicates that you have higher phase angle value. Because as I said earlier, that if you have a higher phase angle value, then it means that the bonding or the interaction between the metal surface with the inhibitor is actually quite strong. Okay. Right. So inhibition efficiency can be calculated as, I think, a previous formula. Any questions so far regarding on this?
Doctor, could you accept Jihad?
He just joined.
Yeah, he said, please tell the doctor to accept my request.
Okay. All right.
Okay, thank you.
So another thing that I would like to explain before we move to Wobble impedance is that when you do the electrochemical measurement for impedance, the placement between working electrode and also reference electrode is important. Okay, so for EIS measurement, okay, the placement of working electrode to reference electrode must be consistent. Okay, this is actually very much important. Okay, to avoid RS shifting. So what does it mean by RS shifting? Okay. So RS shifting is when you do impedance, for example, one sample, you'll get a Nyquist plot like this. Maybe if you repeat the same sample, suddenly it forms like this when you overlay. Then you have a shifting over here. RS. This is RS. The first point I told you is RS, right? You have a shifting of RS. Okay. So this as I said, because of the placement of working electrode and reference electrode is not consistent. So that is why whenever you do the electrical chemical impedance measurement, you have to make sure that the distance of okay, distance of WE to RE must be consistent. So how you can achieve this? The distance of working electrode to reference electrode, the consistency can be achieved if you use stopper. Okay, rubber stopper. For example, if you have a cell like this, we put a stopper, then you put your electrodes here, here, here. Then you have an equal distance, isn't it? The same thing if you put your circuit. Oh, sorry, you put your working electrodes in the bottom. We put stopper here. Then you have a fixed distance. Not only stopper, you can also use electrode holder. That is. To tell you the truth, I experienced this long time ago, maybe back 10 years back when I did impedance. Yeah, I actually just want to share with you, when I did my master's, I was among the first who did EIS in School of Chemical Sciences, because at that time, no one have ever run impedance. I think in those days, for corrosion, people just use potential dynamic polarization. So at that time, my previous supervisor, Professor Muhammad Jain, he actually purchased a potential stat with a function of EIS, and I actually become the first person to do this. Okay? So when I do the when I did the experiment, I noticed that there's a shifting, which initially I don't know what's happened. And many years back, we have a visiting professor in the School of Chemical Sciences, Professor Frank Walsh. Actually, if you have time, maybe you can Google this guy. He's still like in service. Okay, Frank Walsh is actually a professor of electrochemistry, okay, in the University of Southampton, UK. In I think in the world, University of Southampton have a very renowned electrochemist. If you go to UK, if you want to further your studies in electrochemistry for PhD or what, I would recommend you to go to University of Southampton, because I think they have a very good facilities. They have a center of electrochemistry, and I think their professor or researcher is actually a well-known researcher. So at that time, I guess in 2008 or 2009, Professor Walsh was a visiting professor in School of Chemical Sciences. I think he spent like a few months in our department, and we had a meeting. We just like discussing about impedance, because he is actually an expert in impedance. So I was like discussing about this phenomenon, the shifting and everything. So he actually told me, maybe you just need to fix the distance between your working electrode and reference electrode. So when actually been advised to do so, I just like put a stopper, and then figuring out what will be my circuit design, and then a cell design, and after that the problem have resolved. So whenever I do repetition, it's no longer produce a shifting of RS. So yeah, I mean, this is actually by experience. And of course, if like you guys, you learn about the theory before the practical. In my case, I actually see the experiment first. I learn the practical first before I learn the theory. So when I learn the theory, it's quite easy for me to understand, because I've already seen it. Okay. So is there any question before we move to Wobble impedance? Anything that you want to ask?
No, doctor, it's a great job that you learn from the experience first, because you know how that happened and all that. It's good.
And there's also another story that I just to tell you. When I did my master's at that time, there's also another person who did master's, but with other groups, to study impedance as well. And she was sent to France to study about impedance, and perhaps after she been attached like for 3 months or what, she come back and teach us how to do the impedance. But I mean, when she did the attachment in overseas, I was like doing it trial and error. I was like fixing the potential, I mean, the frequency values, just to get a nice data and whatsoever. And what happened is that after she finished her 3 months attachment, she come back and actually learned the impedance from me. Learn how to run the impedance from me. So it's kind of a strange, I don't know, maybe she was not being exposed too much on impedance, but that's it's actually the purpose. But yeah, it's kind of a good memory as well. And I think we are proud to say that in Malaysia, we are among the first who, I mean, in USM, School of Chemical Science, we are among the first who actually studied impedance in Malaysia. I think previous years, I don't, because impedance was developed in the theory is actually developed even earlier than that. But for corrosion, it was like been tested in 90s, if I'm not mistaken, maybe in US or UK. But in Malaysia, came a bit late, maybe early 2000 or something like that, that people started to use impedance as a tool to measure corrosion. But I mean, we are among the first. And now I guess maybe a lot of people, even in UTP and UMP, UMT, UNIMAP also started to use impedance to measure corrosion. Right. So, okay. Any other question? Anything? Okay. So we are moving on to the next part for electrochemical impedance. This is actually Wobble impedance. So Wobble impedance is basically a special types of phenomenon where it occurs whenever you have an effect of diffusion. Okay, so diffusion, you must relate it with Wobble impedance. All right. So the rate of electrochemical reaction can be strongly influenced by the diffusion. Okay. So if you still remember how diffusion happens and why diffusion happens. Mahdi, you still remember how diffusion happens?
Because not electrostatic is immigration.
Not
because the concentration. Because the concentration.
Yeah.
Yes.
I just would like to, keep asking, like how this process happened. Like why migration happened, why diffusion happened, so that you will put it in your mind, the reason why it happens. Diffusion happens actually because of concentration gradient. Okay, and concentration gradient actually happens when you have a saturation. Okay, saturation of interaction. The saturation that I'm talking over here is that most of the anions have been occupied. The vacant space on the working electrode surface, because this is actually space. Okay, so this actually happens when you have how to say a migration or electrostatic interaction first, and then after electrostatic interaction, what happens is basically you will have migration, and then after that difference of a concentration or a concentration gradient, which eventually created so-called diffusion. Okay, the ions have been like pushed to go closer or to move closer to the surface, and the surface is actually been covered mostly with anions, right? This is often the case when a solution species must diffuse through a film. Okay, the film that I'm talking about is now due to the formation of anions being absorbed on the surface. This situation can exist when the electrode is covered with reaction products, adsorbed solution components, or prepared coating. So remember, Wobble impedance can happen due to diffusion, and why diffusion happen? This is actually due to the formation of reaction product, outside layer, passive layer, or adsorbed solution component like the formation or monolayer formation of anions on the surface, or a prepared coating or a coating. Okay. Whenever diffusion effects completely dominate the electrochemical reaction mechanism, the impedance is called Wobble impedance. Okay. For diffusion control electrochemical reaction, the current is 45 degree out of the phase with imposed potential. With this phase relationship, the real and imaginary component of impedance vectors are equal at all frequencies. In terms of simple equivalent circuits, the behavior of Wobble impedance, a 45-degree phase shift is midway between that of a resistor and a capacitor. So there is no a simple electrical equivalent for Wobble impedance. Okay, so what makes Wobble impedance is slightly special as compared to I think as compared to the normal impedance is that it forms semicircle, and after semicircle it forms a 45-degree linear line. I think my slide is not responding. I'm not sure why. You guys can hear me?
Yes, doctor, we can hear you.
Yes, doctor.
Okay. Sekejap, I think I need to stop share first. This is actually what happened if you like oops, close. Very sorry, because sometimes this problem happens mainly because of I'm using a tab. I mean, like a writing tools. So sometimes it's not responsive, and I have to like write all over again. But I guess maybe you guys can capture what I have wrote before this. Fusion. Okay, is actually due to concentration gradient, and concentration gradient actually happens due to saturation of anion on the vacant.
We cannot see any slides.
Oh, okay. I have not shared it. Very sorry. And so Jihad is already here. Jihad, how are you, Jihad? Maybe not, mic is not functioning. Okay. Saturation. Okay.
Hello, how are you?
Yeah.
How are you, doctor?
Good. Saturation of anion on the vacant surface of working electrodes. Okay. So as I said earlier, that Wobble impedance happens if you have a reaction product. This is actually due to the formation of metal oxide, okay, or adsorbed solution component. This is actually the things that we discussed just now, saturation of anions, and also prepared coatings. Okay, right. So the explanation due to the Wobble impedance is like this. You have saturation, okay, that occurs in the inner Helmholtz plane region. This is IHP. And then due to this will create a diffusion. The surface now is being covered with negatively charged anions. And then the counter ions, positive polyatoms of what, will be pushed. Okay? Will be pushed to go near to the surface. Then this actually creates a so-called diffusion. So diffusion actually accounts, as what I've told you, what types of double layer, what models of double layer? Anyone still remember? For diffusion. Helmholtz? No, Helmholtz is actually electrostatic.
It's going Chambon.
Yeah, go Chapman.
OHP. Oh, go Chapman.
Okay, Go Chapman model. So Go Chapman model actually accounts for diffusion. If you still remember, the proposal from Go Chapman is that it says the ion is actually go near, it's actually infinite, it's going near, it's not like aligned together as what been proposed by Helmholtz. Helmholtz actually account this one. Okay, so Go Chapman actually accounts diffusion. So when you have like a diffusion, then the positively charged ion is actually being attracted, but it didn't form like a uniform layer. So it's just formed like maybe some arrangement, not really monolayer or what. But this actually will create a resistance that we call it as Warburg resistance. So if I translate this into electrical circuit model, imagine that this is your working electrode and further here is actually your reference electrode. The interface between these two, if you have an effect of diffusion, you will have still charge transfer process, because charge transfer process is actually where the electron being transferred. Double layer is actually by the formation of the layer, the first layer. And then you have a diffusion layer. This is actually due to the effect of the other species being pushed or diffused to the surface. Then diffusion actually occurs at outer Helmholtz region. And this will create another resistance known as Warburg resistance. And further to reference electrode, you still have your solution resistance. I think parameters or component. This will be the Nyquist plot design if you have Wobble impedance. As I said to you earlier, how to indicate Wobble is very simple. You'll see that, okay, in your Nyquist plot, it will form a semicircle, and after semicircle, it will form a 45-degree linear. And what is actually been mentioned here? I think the explanation of 45 degrees is because it's out of the phase. So semicircle actually indicates charge transfer, and when you have charge transfer, this is actually the yes.
Can you 45 with which between who and who 45 degree?
Sorry again. Yeah.
Can you
this one?
Yeah.
If you see this actually 45 degree here, the increase actually 45
between linear line between this diagram and linear line. Between this diagram and linear line.
Yes.
Yeah, I understand. Thanks.
Okay. Right. So when you have a charge transfer process, this is actually the rate determining step. So that is what is known to be a kinetic control process. Meanwhile, if you have a 45-degree increase, this is actually a mass transfer control. Now, the process is being determined not due to the charge transfer, but actually by mass transfer. Because I told you, the process or the pattern that you get over here is due to the diffusion fact. Okay. So now, this one is actually been considered. Right? So basically, if I ask you again, if you have like maybe this one, the kinetic control actually occurs where? This is actually at the this one, RS is near to the outer hem holes, and then RCT is actually occurs at the inner hem hose region. Okay, so mass transfer is actually occurs in between. I mean, in between inner hem holes and also outer hem holes. Right. So the circuit model is as follows. Okay, and we call this as Wobble circuit. Right. So what will be the Nyquist plot look like? So it will be like a semicircle with 45-degree increase. Okay. And for the Bode plot, you will notice that you have a slight slope over here. So this is actually, you have like one flat line over here. You have almost a flat line over here. Oh man. Now you cannot see the slides.
tak boleh tu.
Oh, doctor.
MashaAllah, how you know, Doctor?
I think today is very bad. I'm not sure why. I think maybe my tab, I should like stop using my tab. I think I told you the tab is actually the one that I used to write in the slides. So that is why you see like handwriting and everything. But actually, it's important because otherwise I cannot explain it in details to you guys. All right. Okay, so this is actually what I'm telling you guys now. You have like the two flat lines, which is actually indicates that you have R over here. This is actually equals to your RS. Okay, RS. And almost a flat line over here is RCT. And you have a slight slope, a slight increase. So this is actually due to your wobble. Okay. In fact, if you look over here, you have like one capacitance and you have one slope. So if you have like these two phenomena, this can actually indicate that you maybe have wobble component. But it's always easy to see from Nyquist plot that you have like semicircle and 45-degree linear line after that. Right, so this is basically the component for equivalent circuit. I guess I have like mentioned to you guys. It's just a recap that you might have a resistant or solution. You can also have a double layer capacitance, polarization resistance, or charge transfer resistance, RCT. Remember, RCT and RS is RP is the same thing. Okay. All right. Diffusion, maybe wobble, and coating capacitance if in the case of if you have coatings. We are going to see the examples later on regarding on coating, inductors and whatsoever. I guess the other explanation you can read it out, but this is just to explain that when you do EIS, you will have different electrical component or circuit element, right? So common equivalent circuit models for corrosion, we are going to use Randall's. As I said, if you have like diffusion effect, depressed effect, then you will use Randall's CPE, constant phase element. Okay. If you have like diffusion, then you will use Warburg models. Okay. So this is actually to sum up the advantages of Nyquist plot and also Bode plot. So I guess this is quite important for you guys to remember, because some people, when they do EIS, they are more prefer to see Nyquist plot because it's easy to see the pattern. If you have like two semicircle, you know that, oh, we have a coating. If you have like semicircle with 45 increase, then you have, okay, we have wobble. And some actually prefer to use Bode, but to me, I actually prefer both. Because for Bode plot, normally it will be easier for me to indicate what will be the electrical component. For Nyquist plot, it will be easier to explain the phenomena. If you add corrosion inhibitor, you will see like which one will produce a bigger semicircles and whatnot. So as I say, it's important because in your exam or in your test, sometimes I will test you what will be the advantages of Nyquist plot over Bode plot, or advantages of Bode plot over Nyquist plot. So Nyquist plot have several advantages. The primary one is that the plot format makes it easy to see the effect of ohmic resistance. You can see it easy because you see a semicircle increase if you overlay. So you can indicate, oh, okay, when I add this corrosion inhibitor at different concentration, I have this kind of trend. Okay. If you take the data at sufficiently high frequency, it is easy to extrapolate the semicircle to the left, down to the x-axis to read the ohmic resistance. The shape of the curve, often a semicircle, does not change when the ohmic resistance changes. Consequently, it is possible to compare the results of two separate experiments that differ only in the position of reference electrode. Okay. The other advantage of this plot is that it emphasizes the circuit component that are in series. If you see, series, if you have like a vertical line that you know it is a series circuit design, then you can immediately know that, okay, this is actually having a series circuit component. And the Nyquist plot format also have disadvantages. For example, frequency does not appear explicitly because, as what I told you, for Nyquist plot, it is a plot between imaginary versus real. So you cannot see, the process occur at which frequency. Secondly, although the ohmic resistance and polarization resistance can be easily read from the Nyquist plot, the electrode capacitance can be calculated only after the frequency formation is known. As shown in figure, the frequency correspond to the top of the semicircle can be used to calculate the capacitance if RP is known. Okay, so meanwhile for Bode plot formats lets you examine the absolute impedance, modulus Z, and the phase shift of the impedance, each as a function of frequency. Bode plot has some distinct advantages over Nyquist plot. Since frequency appears as one of the axes, it is easy to understand from the plot how the impedance depends on frequency. You can actually see where does resistance solutions forms, when does the charge transfer resistance form. Okay. The plot uses logarithm of frequency, log frequency, to allow a very wide frequency range to be plotted on one graph, but with each decade given equal weight. Okay. And the Bode plot also show the magnitude, modulus Z, on a log axis so that you can easily plot the wide impedance ranges on the same set of axes. This can be advantage when the impedance depends strongly on the frequency, as a case of capacitor. All right. So yeah, for Nyquist, for Bode plot, this is what you will expect. You can actually see how does the pattern of resistance and the capacitance look like. Okay, I guess this one is more or less to see, to explain the correlation between the double layer and also the frequencies. You can read it up. I guess this one is just for your explanation. For your understanding. It's not really to be tested during your exam or test. Okay, I believe for this part, the equivalent circuits model for coating and whatsoever, we are going to continue next week. Since I guess, yeah, we still have like 1 week before we end our part. Okay, so I guess, yeah, is there any questions so far regarding on Wobble and also EIS?
Doctor, next week we have to lecture also.
No, actually next week we are going to have lectures on Tuesday only. But actually next week you will have your mid-semester break, right? But
Yeah.
I guess we'll try to like have a lecture next week because we are a bit delayed. Okay, so thought of maybe next week if we can like next week Tuesday we can finish the whole thing. Then maybe after Raya break or after Eid break, you will have your test, and after that, Dr. Faiz Bukhari will take over the session. Okay. So I've not yet decided on your test, the date, but of course I can tell you that it will be after Eid lah. So since most of you are going back to hometown, so I don't know, maybe we will have the test via online or what. Okay, but I've not decided yet. Okay. Any question so far?
It's okay so far, Doctor.
Okay, so all right, then I will adjourn the class.
Doktor, saya ada soalan.
Yes. Go ahead.
Okay. Satu, untuk Wobble ni, dia mostly akan ada RS.
RS ada. Still, we still have a resistance solution.
Memang akan ada lah. Selalunya memang akan ada.
But it's depend. I guess what I have not explained to you because this actually depend on the sample.
Okay.
Sometimes we can also run impedance with solid state, which means the electrolyte is actually a solid electrolyte. Sometimes also we can run the sample using a liquid sample. So I think for corrosion, it's always going to be like liquid sample. That when you have liquid, then you will have a resistant of solution. Okay. But in the case of if you do solid state sample, I mean like this of corrosion, this more like if you want to check the conductivity of your solid material, you can use impedance actually because it can actually measure the resistance, and from the resistance you can calculate conductivity. So with this one, you will not have resistance of solution, but you will observe that it will form 45 degree, and this is actually due to diffusion. So it depends on the sample. If you ask me whether for Wobble is going to have like RS or not, the answer will be it depends on the type of the electrolyte. In the case of corrosion, it will have RS. Okay, because the electrolyte will always going to be liquid electrolyte. But if we are talking about impedance for other purpose, for other measurement, for like solid state, for supercapacitor application, for polymer electrolyte application, this actually doesn't have RS.
Okay. Okay, ada lagi satu.
Yeah.
Okay, slide 55.
55. This one?
Okay, yeah, this one. Okay, from the Bode plot, we will see that the differences in the concentration of the corrosion inhibitor.
Yeah.
What if we have difference analyte? Will we have a difference in RCT? In RS or not?
Of course, yes. Which means if you substitute, you're not going to use HCl, for example, and you use, for example, water or NaCl solution, then it will produce a different RS value.
Okay.
Yeah, because each electrolyte have its own unique resistant value. So for like water, maybe, but more or less what I can tell you is that for conducting materials, electrolyte like water or anything that is dissolved in water, it is normally conducting and the resistance will be very low, like 2 ohms. So like water, we know that it's conducting. And if you have like something dissolved in water also or dilute in water also will be like, yeah. But the value is not going to be the same, maybe slightly different.
Okay. Okay. Dapat dah. Thank you.
Okay. Any other question? Okay, so if no further question, then I will adjourn the class. Thank you very much for your kind attention. I'm sure that you guys have been like headache with a lot of information today, a lot of things need to understand. But if you have anything, you can just like ask me directly. Yeah, and forgot to tell you that after this, I will upload your quiz for this week. So the due is still like 10 p.m. tonight. Then if no further question, thank you very much. Hope to see you next.
The quiz?
Sorry? Yes, today there's a quiz.
Oh, okay.
Okay.
Today we do this, Doctor, also?
Quiz, yes, quiz.
Okay.
Okay. All right.
Doctor,
So thank you very much,
quiz.
guys.
Doctor, quiz on today's chapter, is it?
Quiz. I think last week, I think I have asked you on mixed potential again.
Yes.
Yep.
Yeah. So actually, we have. I have not sent you a quiz on polarization. I mean, like potential dynamic polarization or cyclic polarization. So, yeah, maybe you will have a quiz on this one. And for impedance, we are going to have it probably next week.
Okay, Doctor.
Okay?
Okay,
All right.
Doctor.
Okay,
Bye-bye.
Doctor.
Okay, Doctor.
Once again, thank you very much.
Doktor, maaf.
So, yeah,
Doktor,
we'll see
nak tanya.
you next week. Okay.
How far you
Tomorrow we
have a weekend, Doctor? Thanks.
Doktor
Okay.
nak tanya tentang manual untuk lab besok. Adakah?
Yes. Manual, I will upload it today as well. Don't worry.
Okay. Thank you so much.
Sorry, I forgot to tell. Okay, all right. Okay, guys. See you. Goodbye.
See you. Bye-bye. Have a nice
Doctor.
weekend.
Bye, terima kasih, Doktor.
Okay.
Doctor, which
Okay.
lab, Doctor?
I will inform in the group. It's
Okay.
K011.
3011. Okay.
Ground floor, Okay.
Okay, thank you so much, Doktor. Bye-bye.
Okay, bye.
Bye.
Okay. Banyak kali bye ni. Okay.